Alright, let's get started on the new week 2 material. So week 2, day 1, this would be if we were in class, this is what we would do. I would start you out with this activity. So therefore, when you go into D2L, you will see that this sheet has been loaded up, and at the very top of it, it is called number of divisors. So number of divisors would be what we would do in class. We would spend quite a bit of time working on that. I would let you work in pairs or in groups and think about things. So we're going to do a couple of the examples and talk about them, but clearly I don't have enough time to go through all of this. So you'll need to do some of it and load it up and send it to me to show that you did your in-class work today. So here's what it says. Complete the following steps for each set of numbers. And what you'll find is each set of numbers has something in common. I'm not going to say what exactly, but each set has a different thing in common. So first thing you want to do is generate a prime factorization of each number. Second thing you want to do is list all the factors of the number. Third thing, determine the number of factors for that. And then at the bottom of each group of numbers, you will have this thing. What connections do you see? What's going on? Do you see any patterns that will help us do stuff in here? So a little bit of what we're doing this week will be, well, a good bit of what we're doing this week will be about patterns. And so you need to make sure that you can start seeing these. So we're going to do a few. I think I'll leave this front page to you. That's why I already had it flipped over looking at other stuff. And I'm going to talk to you a tiny bit about what's going on with some of the stuff that I see. So for instance, the numbers that they have are 6, 15, and 77. So it's interesting that they've listed those all together. Let's do that. So 6, the first thing I actually do is I'll go ahead and list all of its factors because I think that's pretty easy. If you would rather go ahead and do a prime factorization of each one, then do that. I'll show you how. I don't really care. You just fill in the blanks, however, whichever order you go into. So, of course, we already talked a little bit about some of these numbers. 6 is 1, 2, 3, and 6. So I can see 1 and 6 pair up and 2 and 3 pair up, and I know 6 is not prime. So therefore, I think I'm pretty good. If you're not sure if there are any other numbers that are less than 6 that are factors of 6, then try them all. Does 4 go in evenly into 6? That's what factor means, right? So let's get a little definition in here. A factor is a number that will divide evenly into the original number. And when we say evenly, we mean there's no remainder, right? No leftovers going on over there. So that's what a factor is. It's one of the things that goes into. A divisor is the same basic principle. People often get these factors confused with multiples. So we'll talk about multiples later. But right now we're talking about all of its factors. So all of its factors are 1, 2, 3, and 6. Okay, now the next thing it asked me to do was to find a prime factorization. Actually, that was probably the first thing. But I'm doing it like this because we already did factors earlier. So prime factorization, and there's lots of ways to do prime factorizations. Again, I don't care what technique you take as long as you can do it repeatedly. So prime factorizations, I like to do the factor tree. So 6, I can see that it's divisible by 2, and so 2 is a prime number and 3 is a prime number. So 2 times 3 is 6. That means that those two are the prime factorization of 6. So I can just kind of be done with that. Okay, so here in my table, I can put the prime factored form is 2 times 3. And I know that it's 1, 2, 3, and 6. And then they asked me to tell the number of factors, and I can see, oh, there are 4 factors in there. 1, 2, 3, 4. So I've got that. All right, next. 15. 15 is 1. 2 doesn't go into 15, but 3 does. And I know it happens to be 3 times 5. And the 15, of course, matches up with the 1. So 1 times 15, 3 times 5, those are the things. If you're not sure, again, double check. I can tell, by the way, that right in here, the 3 and the 5 match up. There's not much in between that could possibly be a factor. It's only 4, so 15 is not divisible by 4, so I know it's not. You could check in here too, but you can see that would have to be 7.5, right? So they don't match up at all. So 1 and 15, 3 and 5. Let me do this. Okay. I think you'll see a pattern by the way I'm matching things up, hopefully. Okay, prime factorization. Again, I'm going to do the factor tree. So 15, I look at it and say it ends in 5, so that means it's divisible by a 5. And that was 3. If you happen to know your divisibility by rule for 3, then you could have done that, and we will get there pretty quickly because we're going to be talking about that today. So if you don't know divisible by 3, don't worry about it. We'll get it today. So again, back to my form. 15 is 3 times 5. I usually try to list the smallest prime first, but if you don't get there, that's okay. 1, 3, 5, and 15. Again, I see there are 4 factors. Perhaps we might see a pattern starting to form. Let's do one more. Well, there's only one more in this set. 77. Now, 77 is kind of big, but hopefully we're starting to pair things up by now. So I know that 1 and 77 are going to pair together, right? And then you can go through and you can check, but 2 does not go evenly into 77. 3 does not divide evenly. 4 does not divide evenly. 5 does not divide. Oh, 7. If you weren't sure, play with it until you see. And 7 and 11, probably most of you know your rules for 11s. Most of you know that if you've got a double, that it's probably divisible by 11 whenever you look at it that way. So 7 and 11 pair up, so that's cool. If I check again, let me think about this. The only numbers again between this pairing are 8, 9, and 10. Well, 8 doesn't go because it's not even, and 10 doesn't go because it's not ending in a 0. So really all I would have to check is 9, and most of you probably know your multiples of 9 up to 99. So it does not go, so hey, that's pretty cool. And when I look at 77, it's prime factorization. I know 7 is a prime number and 11 is a prime number, right? So, alright, I'm seeing some pretty interesting little pattern going on here. So this is 7 times 11. This is 1, 7, 11, 77. And again, there were 4. Okay? So maybe we thought, hey, we were going 2 and then 3 and then we're going to go 5, but we're not. We see a skip in the pattern there. That's not the pattern. The pattern is, I think, pretty clear that these all have 4 factors. And whenever I see that, I look back here at the prime factorization form and I say, what I think is happening is it has 2 unique prime numbers that are in its prime factorization. None of them are squared. It's just 2 times 3 or 3 times 5. So I see that none of those are squared. They're just 2 prime numbers times each other. And look right here in the center of my factors. Those that matched up in the middle, those are actually the prime numbers, right? So it's really 1 and the number itself. And then the only other factors that I have are the 2 prime numbers that are in there. So this particular problem is asking me to list one more number that has the same number of factors. Can you think of one? If I'm right, then what we need is 2 prime numbers. So let me get 2 prime numbers. I'm going to try not to be too big of numbers because I need to do this in my head. And I don't necessarily want to go in a weird pattern, so I'm going to pick 3 times 11. Okay, so I'm going to make the number that is 3 times 11. That's not too big. I can do it in my head. That's 33, right? So if I'm correct and my pattern is correct, then what I think is happening is, again, I should be able to continue this pattern on down. 33 should give me 4 factors. 1, 3, 11, and 33. Sure enough, they do. And I should be able to see that 33 factors prime factorization in the exact same way. It's going to be a 3 and 11. But wait, I knew that because I picked those prime factors, right? So don't pick 9. 9's not a prime. A lot of people do that, and I know it's tempting. But sure enough, here we go. 1, 3, 11, 33, and there were 4 factors in there. 4 total factors. So you can see that what they're trying to do in this activity is to make some kind of a connection for us between how does the number factor prime factorization wise, and what does that tell me about the number of factors that they have. So real quickly, let's look just below that, and here again I think 2 prime numbers gives me 4 factors total. That's what I think my pattern is there. It didn't ask me, but I'm writing it there. So real quickly, let's look at 12 because it's down here in set C. And every time you see that they've got these grouped in different sets, that's going to be a different kind of thing happening inside of there. So let's look at 12 real quickly and see what's going on with 12. He's not going to have, we hope, he's not going to have the same pattern as what's going on up above. So let me think about 12 for just a second. 1, 2, 3, 4, not 5, but 6 and 12, right? And again, I can pair these guys up. Make sure we see, I didn't do it there, but make sure we see exactly which ones were paired up. 12 is not a perfect square, so I shouldn't have anything in the middle, so good. We have 6 total factors or 3 pairs of factors. Let me do the prime factorization for 12 because it's going to be different. And you can do your prime factorization, your factor tree any way you want to. I know that 12 is 4 times 3, and I know that 4 is not prime, so I'm going to make that one split out into his factors. So 4 is 2 times 2, and 12 becomes 2 times 2 times 3, right? So real quickly, let's look at that prime factorization. Okay, we know that that's 2 times 2 times 3. Those are all the prime factors that multiplied to give me 12. But a lot of times I don't want to leave this like this because I'm going to say, hey, wait a minute, that 2 is being repeated. So instead of that, I'm going to use my exponents. That's one of the things about a prime factorization. That's 2 squared times 3. That's his prime factorization. All of these were up here were easy because that was just 3 times 11. That's an easy prime factorization, right? But this one's a little more complicated because it does have the exponent. So I say his prime factored form is 2 squared times 3. And then whenever I list all of his factors, I already had that. 1, 2, 3, 4, 6, and 12. I see again that there are 6 factors. So what do you think about 45? You've already seen the pattern going on up here. Hopefully you've got some kind of an idea. I think just kind of seeing what happened up here in set B, and now I'm working on set C, I think that there's going to be some kind of a duplicate going on. So let's do it and let's see what happens in 45. We'll finish out this page. So 45 is, again, sometimes it might be easier if you go ahead and do the prime factorizations. 1, 3, I know 5 goes into that. I don't think 6 goes into it. I don't think 7 goes into it. I don't think 8 goes into it. Oh, wait, 5 matches up with 9, doesn't it? Okay, 3 and 15, and 1 and 45. Again, I can see there are 3 pairs in there. Again, let's play with our prime factorization. So 45, I'm going to go with 5 times 9, just because I like that. I'm going to say, hey, 5 is a prime number. By the way, on my factorizations, I always call them like these are cherries or something like that. It's a tree with a berry on the end. So the berries are the actual prime numbers. That's what I care about. So the 5 is a prime number. That's why you see me circle some of them and not others. And then the 9, that guy's actually not prime. So 9 breaks down to 3 and 3, right? Okay. So again, his prime factorization becomes 3 times 3 times 5. But again, we don't want to leave it that way. So we write him 3 squared times 5. All right. Okay, 3 squared times 5. 1, 3, 5, 9, 15, and 45. And again, I see, hey, there's 6 of those guys in there. Okay. The last one in that set, and then the rest of this whole page, you would do in groups. I would not do all of this leading the lecture, so to speak. I would make you do this as groups. So you can do the last of it and just scan it in and show me that you did it. So, okay, 1 and 50, 2 and 25, 3 doesn't go into 50, 4 doesn't go into 50, 5 goes into 50 10 times. All right, and then I can start pairing, right? So 5 and 10, 2 and 25, 1 and 50. If you know them, some people like to write like 1 comma 50, 2 comma 25, 5 comma 10. You can do that as long as you keep them straight in your head. I just like to do them in order and make sure there's nothing in between any of those. Like I know there's nothing between 6 or 5 and 10. So 6 doesn't divide, 7 doesn't divide, 8 doesn't divide, 9 doesn't divide. None of those divide evenly, right? That's the trick, is the evenly part. They'll go in, but they just won't go in with no remainder. So there we go. I know there are 6 factors. It's going to follow in my pattern. So again, 50 is, I'm going to do 2 times 25. 25 is 5 times 5. Okay. So my prime factorization is 2 times 5 times 5, or 2 times 5 squared. Again, I see this lovely little pattern going on here where one of the numbers is a prime number and the other number is a prime squared. So here it is, 2 times 5 squared, 1, 2, 5, this was a 10, 25, and 50. There are 6 of them. So you guys think for just a second, what is a number that meets this pattern using prime numbers? I can come up with one. It's not in there yet. The way I want to do it is I want to make sure my prime factorization matches up, right? So I'm going to look right in here, and I'm going to do 2 times 3 squared. Do we think that number will match up? It's one prime number times another. By the way, they don't have to have a 2 in them. I'm just keeping them easy, right? Because I don't want to go 7 times 5 squared, because that number is going to get really big. I don't want to do it in my head. So 2 times 3 squared. 3 squared is 9 times 2 is 18. Let's talk about his factors. 1, 2, 3. 4 doesn't divide into 18 evenly. 5 doesn't go evenly. 6, and again, now I've started to pair. 9 and 18, all of those go together. So I see that there are indeed 6. And if I had to write this pattern out, I would say a prime number times a prime number squared. That's what my pattern there is, right? And that will actually, knowing how to do that kind of thing, that we're breaking these down into their prime factorization, will actually help you with the homework for today's lesson. So I want you to kind of look through, make sure you do this entire activity. I started on the second page, but as you might imagine, the first page, there's a lot of them there. They gave you a lot of examples so that maybe you can play with them and see, okay, what all's going on in there. So think about what's going on in there. They're not, some of them are perfect squares, but some of them are not. So 8 is not a perfect square. So you're going to have to think about what's really going in there, break it down into its prime factorization form. If you need to, maybe do something with the, down here, sorry. Maybe do something with the prime factorization with the exponents or something like that. It might help you out. So that's what you're going to do. So far, I've only been talking for about 20 minutes. So you would have time right now to work on this. In class, you would have buddies and you'd be talking to each other. So maybe phone a friend if you got somebody. Work that out. I'm going to stop this video and then we're going to do video number 2 for day 1. And that'll wrap up the day 1 material and get your homework out there for you. All right. So hang on. I'm coming right back.